In this class, I will explain about the dynamics of fluid flow. What is dynamics and what are the different forces acting in a fluid, acting on a fluid which is flowing. And also, we are going to derive an important equation of fluid flow called Euler's equation. And from that, we can derive one more equation called as Bernoulli's equation. So actually, this is based on Euler's equation, Bernoulli's equation. They are based on another fundamental principle of mechanics, that is law of conservation of energy. Just like continuity equation was derived from law of conservation of mass, Euler's equation, Bernoulli's equation, they are derived using the law of conservation of energy. Of course, the basic for that is the Newton's second law. Now let us first define what is dynamics of flow. It deals with the forces causing the flow and the energy involved in the flow. So in kinematics, of course, we dealt with only velocity, acceleration, displacement, path traced by a fluid particle and all. If you consider forces also which are causing the motion and energy involved in the flow, then that will come under dynamics, fluid dynamics. Now let us see what are the different forces acting in general on a fluid which is flowing. So it can be characterized as body force, surface force, linear force, like that. Body force means along the entire volume of the fluid that force will be acting. For example, you can take weight of the fluid as the body force. Surface force means if the force is acting over an area, for example pressure force. It is an example for surface force because pressure force will be acting over an area. Linear force means suppose if the force is acting along the length of the fluid, for example surface tension force. That is an example for linear force. Apart from that, you can classify the different forces acting on a flowing fluid as gravity force. Gravity force is denoted by Fg. It is nothing but the weight of the fluid which is flowing between certain sections, denoted by W. Weight of the fluid is given by gamma into volume, that is specific weight into volume gives the weight of the fluid. So normally in the case of channel flows, the flow will be due to gravity, its own weight. There this force is predominant. Of course in pipe flows also, in some cases we are going to consider the gravity force. Second one is the pressure force, which is more important in case of pipes, because in the case of pipes flow occurs only due to pressure difference between two sections. So and it is given by P into A, where P is the intensity of pressure acting over an area A. Third one is the viscous force, which you can observe in the case of highly viscous fluids, where the shear stress developed will be very high. And the viscous force Fp is given by shear stress developed multiplied by the area over which that stress is acting. Normally in the case of boundaries, pipe walls or channel boundaries, this is when the fluid is very high viscous. In such cases you can have this viscous force. Next, the turbulent force which you can experience in the case of low viscous fluids like water, where turbulence effect is there. Surface tension force, when the depth of flow is very less, then in such cases when thin sheet of water is flowing, then in such cases surface tension force may be predominant. For example, flow over Vs and all. Then you have compressibility force, which you can expect only in the case of compressible fluids, mainly in gases. In liquids, this force you can neglect because the compressibility effect in the case of liquids it can be neglected. So we are going to derive an important equation called Euler's equation of fluid motion along a streamline. In that case, we are going to consider only pressure force and gravity force for the analysis. The rest of the forces, they are neglected. Now Euler's equation of fluid motion along a streamline. So we are going to take a streamline. Along that streamline, how the flow takes place and what are the different forces acting on that streamline, that we have to consider, and then by applying the Newton's second law of motion, that is F is equal to m into A, where F is the resultant force acting in the direction of flow, and m is the mass of the fluid, and A is the acceleration of that fluid which is in motion. So before going for the derivation, we have to assume certain things, assumptions to make the derivation simpler. So fluid is non-viscous, homogeneous and incompressible. So density remains same, that is the meaning of incompressibility, and physical properties remain same, that is called as homogeneous. And it is non-viscous means you can take it as an ideal fluid, viscosity is very less, like water. Second assumption is flow is steady, continuous and rotational. So steady flow means the fluid properties, they don't vary with respect to time over a period of time, and the flow is continuous, so there is no obstruction to the flow. And irrotational means, as I already told, the fluid particles, they won't rotate about their mass centers, or it is a potential flow, we can say. And the third assumption is velocity is uniform, that is, it is uniform flow. So velocity remains same at all the sections. Then the fourth one is the only pressure force and gravity force are considered. So the other forces are neglected when you are deriving the Euler's equation. Now I consider a pipe containing some liquid with specific gravity, specific weight gamma flowing in this direction. So I have taken like this. 1 and 2 are the two sections which I have considered. With the distance between 1 and 2, I will take it as ds, and this inclination whatever I have given here, so this elevation difference between 1 and 2, it is dz, and ds is the length between those two sections, and I will take the pressure at 1 as P1 and the pressure at 2 as P2. So cos theta, according to this figure, you can see if this angle is theta, then cos theta will be, I have written here, cos theta will be dz by ds. You can use this relation. Now, this is a streamline. I have taken a streamline here. So whatever I have shown here, this is the streamline. Now what I will do here is, along the streamline, I will derive the equation of fluid flow, that is the Euler's equation. So I have written another sketch here showing the streamline, and I have resolved this W. So here we have to consider only the pressure force, that is force due to P1 and P2, and also one gravity force. Gravity force is nothing but W, the weight of the fluid which is contained between 1 and 2. That if I resolve that weight component, so along the direction of flow, so this is the direction of flow. So along the direction of flow, if you resolve that, you will get W cos theta as the component. Now, in this diagram, carefully observe this diagram. So this G is the centroid or the center of gravity of the weight of the fluid which is contained between these two. At that point, W is acting. If you resolve that, W cos theta is the component of this W acting in this direction. This is the direction of flow. So it is flowing like this. So P1 is the force at this end, pressure at this end, P2 is the pressure at this end. And V1 and V2, they are the velocities at 1 and 2. But since velocity is uniform here, V1 will be equal to V2 and that is equal to V. Now, W you can get this is nothing but the weight of the fluid. As you know, weight of the fluid is given by the product of specific weight of fluid and the volume. So here specific weight is gamma, and volume of the fluid contained in this region is ds into dA. dA is the area, elemental area over which that pressure is acting, and ds is the length. So length multiplied by the area gives the volume. So gamma into dA into ds gives the W value. Now the intensity of pressure is P1 and P2. If you convert that to pressure force, that intensity should be multiplied by the corresponding area. Here the elemental area over which this P1 is acting, this area I am going to take it as dA. Here also this area I am going to take it as dA. So P1 into dA, P2 into dA, they are the pressure forces acting of the fluid in at 1 and 2. Now I am going to apply the Newton's second law of motion. So here, according to that, sum of the forces acting along the fluid flow direction is equal to the inertia force. That is sigma F is equal to m into A. So that is the equation. Sigma F, resultant force acting on the fluid in motion, will be equal to the inertia force, which is m into A. Now if you substitute the forces expressions in the LHS and RHS, and if you simplify, you are going to get the Euler's equation. Now let us see what are the, now I will take along the direction of flow, means I will take in this direction. So forces acting in this direction. So here P1 into dA, that is the force acting in the upward direction, so that is positive, and P2 into dA, it becomes negative. So this is positive I will take, and the forces acting downwards I will take negative. So P1 into dA minus P2 into dA becomes downwards, and this W cos theta is also acting in the opposite direction. So it is negative minus W cos theta is equal to m into A is the inertia force. Now let us, this is the Newton's second law. Now we have to substitute for all these things. So what I will do is P1 I will take it as P, and P2 is P plus dP, because they are different, pressures are different. So P1 I will take it as P, and P2 as P plus dP. There is change in pressure, that is why flow is occurring. And you know that cos theta is dz by ds. Now if you substitute those things here, P1 this becomes P into dA minus P plus dP into dA minus W is gamma into dA into ds into cos theta is dz by ds is equal to, now I have to substitute for m and A. You can see here m is rho into volume. So mass density multiplied by volume gives the mass of the fluid. Similarly your gamma, which is specific weight into volume, this is specific mass into volume. So rho is the specific mass into volume is once again dA into ds. This is the expression for m. And acceleration, you know that it is dV by dt, rate of change of velocity, and this dV by dt can be written as dV by ds into ds by dt as per chain rule, and this ds by dt is nothing but the once again velocity, so this is nothing but v. So I can write this as dV by ds into v. Now substituting for m as rho into dA into ds, and for A as dV by ds into v here in the RHS. Now if you simplify this, if you simplify this expression, P into dA minus P into dA will get cancelled. So another minus dP into dA will be there in the LHS, and here this ds and ds gets cancels. So because they are lengths, so minus gamma into dA into dz will remain. That gamma I have written it as rho into g, because specific weight is equal to specific mass into g. That is the relation. So rho into g I have written for gamma. So gamma is equal to rho into g. So that I have substituted here. And RHS it becomes, here also ds will get cancelled. So rho into dA into dV into v. So like that we are going to get after simplification. Now what I have done here is, to get the standard form of Euler's equation, I have divided both sides of this equation by minus rho into dA. So you should be careful here, minus rho into dA. So if you divide this by minus rho into dA, so rho is not there here, therefore it becomes minus divided by minus becomes plus dP by rho you will get. Okay. Second term will be minus divided by minus becomes plus, that rho will get cancelled, dA will get cancelled, you will be left with g into dz, second term. Then RHS, if you bring to the LHS it becomes minus, once again that minus divided by minus becomes plus, rho into dA will get cancelled, you will be left with only v into dV, and the RHS becomes 0 because I have brought this to the LHS. Now this equation is called as the Euler's equation of fluid motion along a streamline, because I have considered small area, so it is along a streamline. So dP by rho plus g into dz plus v into dV is equal to 0. That is the Euler's equation. You can see here the first term represents the pressure term, second term represents the elevation of the datum term as a reference term, third term represents the velocity term. So there are three terms in this: pressure, datum and velocity. So this equation 1 is called as the Euler's equation of motion along a streamline. Now from this Euler's equation we can derive another equation, very important equation called Bernoulli's equation, which is used to analyze fluid flow problems. So that is nothing but another form of law of conservation of energy. So this Bernoulli's equation is obtained by integrating this equation 1 on either side. So integrating 1 means, so integral dp by rho plus integral g dz plus integral v dy is equal to integral 0. So all the terms you have to integrate. When you are integrating, so since rho is constant for incompressible fluid, because the assumption is the fluid is incompressible. So incompressible means rho is constant. I have told you. So that rho, when you are integrating, you have to treat that rho as constant. Of course, g is also constant as due to gravity. Now here what happens, if you integrate this, 1 by rho you can take outside. Integral of dp is p only. So p by rho plus g you can take outside constant. Integral dz is z plus integral v dv is nothing but v square by 2. So because integral x dx is x square by 2, integral v with respect to v only, v dv is nothing but v square by 2, and integral of 0 is a constant. So RHS becomes a constant. Now still further I can simplify this. Divide both sides by g. If you divide both sides by g, this becomes p by rho into g, plus g gets cancels here. Only z will be there, plus v square by 2g you are going to get is equal to another constant, because constant divided by g is another constant. So you are going to get like this. This can be written in this form. So first I will write z plus p by rho into g is nothing but gamma from the definition, plus v square by 2g is equal to constant. So this equation, so the second equation, this equation is called as the Bernoulli's equation for the fluid motion. That means you can arrive at the Bernoulli's equation by integrating the Euler's equation. So Euler's equation we are deriving for a fluid motion along a streamline, whereas the Bernoulli's equation you can use for solving problems as a whole in pipe flow or channel flow, whatever it is. It contains three important terms here also. So the first one Z is called as the datum head. Second one, P by gamma, is called as the pressure head. Third term, V square by 2g, is called as the velocity head. So the sum of pressure head, datum head and velocity head remains constant in a fluid flow, in an incompressible fluid. Of course, I can say like that. In an incompressible, steady, so you can add all these words. In an incompressible, steady, continuous, irrotational, non-viscous fluid flow, all these terms you can add. The sum of datum head, pressure head and velocity head remains constant. So that is the statement of Bernoulli's theorem, what you can say. Using that you can solve, there are some applications of Bernoulli's theorem like Venturi meter, orifice meter, pitot tube, all those things. You can always analyze fluid flow problems. We can find out the pressure. So whatever unknown is there here, so pressure may be unknown, velocity may be unknown, or elevation may be unknown, z may be unknown. So those things you can always evaluate using this Bernoulli's theorem, and also using the applications. Some devices have been developed, Venturi meter, orifice meter, pitot tube and all. They are used to measure the discharge or the rate of flow in pipes or channels, or they can be used to find out measure the velocity. So very much important in fluid mechanics. Finally, we are interested in finding the discharge or rate of flow in any project, irrigation project, or in any water supply project, or in any other sewage treatment plants design and all. Finally, we are interested in the discharge carrying capacity of pipes or channels, whatever it is. For that, using this concept of Bernoulli's theorem, we can always derive the equations for the discharge and all, which we will discuss later.